All right, let's talk about something every business craves: consistency. It's king, right? But what happens when your workflow is anything but consistent? You're dealing with batch sizes that are all over the place. How in the world do you keep a handle on quality then? Well, we're about to dive into a seriously powerful tool that's built to solve this exact problem with, yeah, surgical precision. So think about it in your world. Maybe one day you're cranking through 100 invoices, and the next day it's 500. Or hey, maybe you're making custom parts, so every single run is a different size. Now, if you find more defects on that massive 500 invoice day, does that mean your quality took a nosedive? Or did you just have way more chances to find mistakes? See, without the right tool, you're basically just guessing. You're flying blind. And this isn't just some nerdy stats problem, it's a huge business challenge that can hide some really serious issues. So, for this very specific problem, guess what? There's an equally specific and frankly powerful solution, and it's called the U-chart. This thing is literally engineered to handle variability. And by the time we're done here, you're not just going to get it, you'll know exactly how to put it to work.
Okay, let's get into it. Section 1, what is a U-chart? We're going to lay down the core concept right now.
So, at its heart, a U-chart is all about tracking what's called attribute data, basically stuff you can count. Think scratches on a car door, errors on an invoice. You get the idea. But here's the absolute key, the game changer. It doesn't just give you a raw count of defects. No. It calculates the rate of defects, the average number of defects per unit. And that one little shift from a total number to a rate is what magically solves our whole variable sample size problem. It's what lets us compare that batch of 500 with a batch of 100 on a totally level playing field. So yeah, that U in U-chart, it literally stands for the average defects per unit. And its superpower, for sure, is handling those shifting sample sizes. Now, if you want to get a little technical for a second, under the hood, it's all based on something called a Poisson distribution. Don't let the name scare you. All that really means is it's perfect for defects that can pop up anywhere, but are kind of rare and don't influence each other. Like a typo on a page or a paint chip on a product. And when you look at the chart itself, it's super simple. We just plot that average defect rate over time. That's how we see what's really going on with our process.
Okay, section 2. The U-chart doesn't live on an island. It's actually part of a whole family of quality tools. And look, to be really effective, to be a good consultant for our own businesses, we have to know more than just how a tool works. We've got to know when to pick it over all the others. And for that, we need a clear, logical framework. So in the universe of control charts, the very first big split, the first decision you make, is between variable data and attribute data. Variable data is stuff you measure, length, weight, temperature. Think of things like X-bar and R charts, but that's a story for another day. Today, we're focused on attribute data, and that's simply data that you count, like the number of bad parts or the number of flaws on a single part.
And this is where we can bring in a classic consulting trick, the MEIS framework. You might have heard of it. It stands for mutually exclusive, collectively exhaustive. All that's a fancy way of saying we've covered all our bases with no overlaps. So for the kind of data we're talking about, your choice really boils down to two simple questions. First, are you counting whole bad items, like a simple pass/fail, or are you counting the number of defects on an item? And question number 2, is your sample size always the same, or does it change? That's it. And as you can see, the U-chart has a super specific job. It is the tool you grab when you're counting defects per unit and your sample size is all over the map. Nothing else does that. All right, section 3. Let's really double-click on that decision point, because honestly, understanding the exact trigger for when to use a U-chart, that's what separates just knowing the theory from actually using it effectively in the real world. Okay, so where do people usually get tripped up? It's almost always comparing the U-chart to its close cousin, the C-chart. But this comparison is perfect because it highlights the one thing that matters most. A C-chart is great if your sample size is always the same. Think about inspecting the exact same size sheet of gloss every single time. But the very second that sample size starts to change, you serve a different number of meals, you process a different number of invoices, you get different size shipments, you absolutely have to switch to a U-chart. That's the only way to get a signal that means anything. The U-chart is what normalizes all that data, giving you that per unit average so you can make a fair comparison. Now, before we actually build one, just a quick but really important sanity check. These are the ground rules. For this chart to actually work and be valid, a few things need to be true. 1, you have to assume that every item has the same chance of having a defect. 2, one defect doesn't cause another one to happen. And 3, and this is huge, your inspection process has to be consistent.
Because if you inspect one batch way more carefully than another, well, you're not measuring your process anymore, are you? You're just measuring your own inspection.
Okay, section 4. We've talked about the why and the when. Now it's time for the how. Let's walk through the actual mechanics of putting one of these together, step by step.
Believe it or not, the process is really logical. First, you just collect your data. How many defects did you find in each batch? Simple enough. Second, for every single one of those batches, you calculate U. That's just defects divided by the batch size. Third, you figure out your overall average, your center line. You just take the grand total of all defects and divide it by the grand total of all the items you checked. That's your baseline. Fourth, you calculate your control limits. Think of these as the statistical guardrails for your process. And then finally, step 5, you just plot everything on a graph. Theory is one thing, but let's make this real. Let's run through a quick example. We've got a motorbike manufacturer, and they're tracking defects over 20 days. Now, the key here is that the number of bikes they roll out and check each day is different. That makes this a textbook case for a U-chart. So, after they crunch the numbers for those 20 days, they find they have 934 total defects across 2,240 motorbikes. Do the simple division, and you get this, 0.417. That number, that's our center line. It's what we call U-bar. And don't underestimate this one little number. It's incredibly powerful. It is the stable, historical average for this entire process. It means that day in and day out, they should expect to find about 0.417 defects on any given bike. That's the benchmark. Everything else is going to be judged against that. Okay, section 5. So you've made the chart, but honestly, that's only half the battle. The real magic, the real value, is in knowing how to read the thing and what to do about it. This is the so what moment. This is where we turn data into actual insight, and insight into action. So when our motorbike company puts all their data on the graph, one point just jumps off the page. On day number 8, the average defects per bike just went wild. It shot way up, clear past the upper control limit. I mean, all the other 19 days are behaving themselves, just bouncing around nicely between those guardrails we set up. But day 8? That's a serious outlier. And you know what? The rule for reading this is beautifully simple. It's absolute. If even one point goes outside those limits, your process is, by definition, out of control. Now, that doesn't mean the whole factory's on fire. It just means something weird, something unusual happened that day, and it needs your attention. And right there, that's the whole payoff of using a control chart. That one little dot represents what we call a special cause variation. It's the signal finally breaking through all the noise. See, all the normal ups and downs inside the limits, that's just common cause variation. That's the predictable, acceptable hum of your system. But a point outside those limits, that's a fire alarm. That's your process screaming at you that something non-random and unusual went down. The chart won't tell you why it happened, but it does its job perfectly by telling you exactly where and when you need to start asking questions. Which brings us to the final and maybe the most important question of all. The chart did its job. It gave you a crystal clear signal. It told you your process is out of control. You've pinpointed a special cause. The data has led you to a specific day, a specific moment. So the analysis part, that's done. But now, the real work begins. So what's your first move?